much energy is needed to change 75 grams of ice at 20 degrees Celsius to steam at 150 degrees Celsius? Common mistake here is for students to simply go ahead and use the equation for calorimetry because there's a temperature change, okay? However, that would be a mistake, okay? Because not only is there a temperature change, there are two phase changes, okay? So let's go ahead and look at the entire process. We're going to start off with ice, okay? And that ice is at a temperature of negative 20 degrees Celsius, okay? And the first thing I'm going to have to do is raise the temperature. But when I get to 0 degrees Celsius, okay, something is going to happen. The temperature is going to stop raising, and it is going to take a little time to melt, okay? So there's going to be a little stop in the temperature change right here while it's melting. Okay? Then after all of the water has melted, okay, then the temperature is going to rise again. So the water's melted, temperature's rising, it's rising, it's rising, and then it's going to stop rising again. It's going to stop rising because it's going to boil. And while it is boiling, the temperature won't be changing. It's just going to be changing phase. And that'll happen at 100 degrees Celsius. And again, the temperature is going to stop changing for a little bit while it's undergoing a phase change. Then after it is all boiled, it's all steam, okay, then the temperature can continue to rise until it gets to the 150 degrees Celsius. So there's a lot going on here, okay? So let's look at each individual section, okay? Right here, the temperature is changing, okay, until we get to the melting spot. So while the temperature is changing, we're going to use our equation mc sub p times the change in temperature, and we always do final minus initial, okay? Then what's going to happen right here is it's going to stop changing temperature for a little while, okay, and it's going to change phase. And during a phase change, we need to use latent heat. In this case, it's going from a solid to a liquid, okay? It is melting. That is the latent heat of fusion, okay? Then after it's done melting, the temperature will continue to rise, okay, until it gets to 100 degrees Celsius. While the temperature is rising, that's because we're adding heat, and we need to use mc sub p, change in temperature, final minus initial again. At 100 degrees, again, temperature is going to stop changing for a little while we're going through a phase change. So it's mass times the latent heat. This time we're going from water to steam. It is boiling or vaporizing, so we are going to use the latent heat of vaporization. Then after it's all steam, the temperature can start to rise again, and it's going to go from 100 to 150. So mc sub p, change in temperature, final minus initial. Okay? All of these are happening. We have to add this heat to get it to go up to 0. Then we have to add the heat to make it melt. Then we have to add the heat to raise temperature. Add more heat to boil it. Add more heat to raise the temperature. So we're adding up all of this heat. And remember, heat is the letter Q. So Q is equal to, and now we can start substituting in, the mass. Okay, well, the mass was 75 grams. We need to make sure we convert that to kilograms. Times the specific heat capacity. You need to look this up. This is the specific heat capacity while it is ice. So the specific heat capacity for ice is 2090. Times the final temperature, which was 0, minus the initial negative 20. Okay? Plus mass, 0.075, times the latent heat of fusion. If we look that up, the latent heat of fusion for water is going to be 333,000 joules per kilogram. Now we have to raise the temperature again. So again, mass 0.075 times the specific heat capacity for water. This is water right here. Okay, that's a liquid right there. So specific heat capacity for water is 4,186 times the change in temperature. It's going, final was 100 minus the initial was 0. Then we need to add in the heat it takes to boil it. So the mass, 0.075, times the latent heat of vaporization, which is 2,260,000. And then again, we're going to raise the temperature. So we have to take the mass, 75 grams, times the specific heat capacity, this time for steam. So the specific heat capacity for steam is 2,010, times the change in temperature. Well, the final is 150 minus the initial is 100. Okay? Then we can go ahead, start simplifying here. So multiply all this together. We get 3,135 plus the second term, we're going to get 24,975 plus the third term, we're going to get 31,395 plus, from the latent heat of vaporization, we have 169,500 joules, plus, when we raised the temperature the last time, it takes 100,575 thousandths joules. We add all of these up, the total amount of heat needed is 329,505 joules. So to change ice at -20 into steam at 150, it's going to take 329,505 joules of energy.